I'll go ahead and start, I guess. This is David Brown. I'm also the session chair for session 1. Please, we're going to do questions at the end of both papers in this section. Just post them to chat. David Bundy is acting as the Q&A associate, so he'll handle getting the questions to Sascha and Jiri. So our first paper is let's put the memory model front and center when teaching parallel programming in C++. I'm going to butcher names. I'm apologizing in advance, but it's Jiri Dokulil, University of Vienna.
Okay, so let's get going. So as you've heard, name's Jiri Dokulil, but it's extremely tricky to pronounce because it's Czech and you need probably 10 years of practice to say it properly. So it's not a problem. Yeah, I'm not going to read the title again and lose another minute. So as you can see, the affiliation is Faculty of Computer Science, University of Vienna, although I put this asterisk at the end because a kind of disclaimer, I no longer work there because of some COVID-related issues. I've ended my contract at the university at the end of March and moved into the private industry, but all the points remain just as valid nonetheless. So it's just a small comment that also, if you wanted to get in touch, the university email from the paper will continue working for quite some time longer. So that's also available if you have some questions and you'd like to get in touch. The address, I think the retention is something like 10 years or some, so that shouldn't be a problem. So let's get going. Kind of the theme of the workshop is this curriculum. So I looked into it to see how they deal with memory models. And there is a section about memory models in the curriculum. So there are these 4 topics that are taught. Two of them are expected to be taught in certain courses. However, this is slightly different view of what memory model means. This is more from the distributed computing world, where you're dealing with synchronizing multiple memories. So you have these real sequential consistencies, relay consistencies, and you're trying to work out what the result is. I'm viewing the memory model from a slightly different angle, from the programming language point of view, not so much these problem distributed systems, although obviously they are closely related, but it's a bit different. So in a programming language, what the memory model mostly does, it describes the visibility of changes made by the commands in the program. So let's say we have a command A, which changes the value of X, and command B, which reads a value of X, and that's possibly in a different thread. And the question is what the B will see when it reads X. So whether it reads the original value before A changed it, whether it will see the value written by A, or whether, which is also quite possible, that the value is undefined, so we cannot tell what the value will be seen. And the main purpose of this memory model is to actually not synchronize some memories, but to restrict operation reordering, because both the hardware and the compiler may reorder the operations in the program, usually to improve performance. Actually, one big problem is that on the hardware, this is not really a problem on the usual x86 or x86-64 architectures, because they basically ensure that the instructions, the results of instructions, are written in the memory in the order they are presented, which, as I said, I mentioned that it's a bad thing, and it's a bad thing because it means that if you don't do it right, from this memory model point of view, it's quite likely going to work out anyway, because the hardware saves you from the problems. However, what's not going to save you and what's completely happy to get you into trouble is the compiler, which will happily move things around. It will also happily put stuff into registers and not read the new data from memory or may propagate changes to the memory. So the compiler can get you into trouble really fast if you're not careful and if you don't deal with the memory model. So the problem is that when the students start, at least from my experience, studying computer science, they quite often have very straightforward view of what the compiler does. So the compiler takes the source code and just translate the C commands into some assembly, and maybe they are aware of some optimizations, so it might, I don't know, find faster instructions or something like that. But they generally don't expect the compiler to move move the commands, so to move things around a lot, to reorder instructions. And also, they quite often don't realize that the variables are stored in registers, so that if they write into a variable, it might not go to the memory for quite some time or at all. So the example I usually start with looks like this, where we have two threads that increment the counter and then print out the value. And then there's quite easy to demonstrate that these concurrent increments of the same counter, that's kind of the textbook example. If you have read, modify, write from two threads, that you could have a nice race condition. But what's much less obvious is that what this printing out of the value of the counter does, because it's quite possible that the compiler will just reuse the value from the increment also for the print. And that might be surprising to some of the students, that they might expect it's possible that both these increments happen at the same time, and then later both of those prints will happen at the same time. So if the counter starts with 0, that they'll get 2 and 2 printed from both threads. And while it's perfectly possible that they might not ever get 2 and 2. So just then I have this kind of what you see is what you get view of their programs. So they have a C code, which is translated more or less one-to-one to assembly, and all the reads read stuff from memory, and all the writes write stuff to memory. So it's relatively tricky to break this view of the compiler. So what I do in our courses is spend quite some time explaining why this view is bad and why they get into trouble really, really fast if they take this view in a parallel program. So as I mentioned, I teach this stuff. So we have a parallel programming course, which is an introductory course. So these are bachelor students in roughly the 3rd semester, but it could be also earlier or later. So this is Introduction to Parallel Programming to students who already had some courses about programming languages, algorithms, data structures, and all this stuff. We have currently 3 parts in the course. The first one is multi-threading in C++, mostly C++ 11. The second part is we show them OpenMP, and finally MPI, because historically we've been teaching MPI to students, so we put this already in the introduction. And the memory model is only covered in the C++ part. So in the first one, and the other 2 don't really deal with this, maybe a brief mention, but not that much. And what we do, we focus on what the compiler does, not on the hardware, so not on the reordering of memory operation that the hardware does, because the compiler already can get you into enough trouble, so we don't even need to consider the hardware to show the students how bad things can get. So the course is held every semester. There are 50 to 60 students. There are 50 to 60 students start every semester, and we also have some practical assignments, and they have to do one of those for each part. So there's one C++ assignment, one OpenMP, and one for the MPI. So this is a brief outline of the course, the different parts of the course, and what a different font is supposed to highlight. If it's in bold, it means that it's mostly about the memory model. If it's in italics, which is only this one, that means that the memory model is somewhat involved, but it's not the main focus of this section. And the rest is that it doesn't really deal with the memory model. So as you can see, the memory model starts fairly early in the course. It's quite important, but it's not everywhere. So that's how we've ended up doing it. So another motivating example for the students, where they also to help them realize how they can get into trouble, is if you have two variables, one with data and the other some kind of flag that says that we're finished, we've computed the data. And if we have two threads, one of them sets the data and then sets the flag, and the other waits for the flag to be true and then reads the data. Then again, I spent quite some time explaining to the students why this wouldn't work if these are just two plain variables, that the compiler might decide that it's going to first write the flag and then the value, so they could see the unchanged data. And yeah, the idea is to show them that they really need to be careful about this stuff. Otherwise, their parallel programs wouldn't work at all. So as you probably know, the C++ didn't really have a memory model until C++ 11. So we also spend a bit of time explaining to the students how things worked before. So if you take, for example, POSIX threads, how could they work without memory model? And that's the combination of the POSIX standard, which requires some propagation of the changes between threads, and also the guarantee that with C library calls, all the writes that are made before the call have to go to memory, and all reads after the library call have to go from memory. So we have this mutex log. We know that these two reads, this unlock, we know these both two writes will finish before the unlock is called. So that's the POSIX thread. So that's just kind of a small example to show the students that there was world before C++ 11. Okay, so then we talk quite early about atomic operations to kind of motivate them what great stuff they can do if they really get into C++ 11 and move from, let's say, the POSIX. And so we introduced this early because it's really nice solution to this counter increment example. But then we also right away warn them about the downsides, so that the memory model on the visibility of changes, also play quite a big role when we deal with atomic operations, so that atomic operations are not just about the atomicity. That's actually the easy part, but the reordering of operations is a really big issue, and it's even worse when we start interacting with non-atomic variables. So another thing that we obviously need to do fairly early is introduce C++ 11 threads, because without those, there wouldn't be much parallel programming. So we do this quite early, but it's also another topic where you can explain to the students that the memory model is kind of everywhere, because if you create or join threads, it also has impact on the memory model, which students tend to understand quite naturally, that if you create a thread, it sees all the changes made in the master thread before it was created. And after you join a thread, you see all the changes made by the thread that was joined. Quite interesting observation is that this is very natural to expect this, but after doing this course, the students might actually doubt it. So I've emphasized it a bit more in the lectures, because sorry, click the wrong button in the lectures, because it showed that in the test, the students might assume that no changes are being propagated into the thread or out of the thread, because in the test, students kind of expect trick questions, so they might find those even when there are none, so they overthink the memory model. So that's one downside of teaching the memory model, that it makes them a bit paranoid. Okay, so then we go into to talk about mutexes, which look almost identical to the POSIX, but they are not, because with the POSIX mutexes, you get a two-sided fence. With C++ mutexes, you don't. There's actually there are release and acquire operations, so they are just one-sided. So we introduce the release and acquire semantics to the students quite informally. But it's quite easy to explain with the mutexes, that you have this chain of write, release, acquire, and read, where you are guaranteed that to see the changes, the read is guaranteed to see what was written. So the mutex is actually quite a good point where we can start showing the students how to use the memory model to properly ensure that the changes become visible when they want them to. So we actually spent a lot of time on the memory model. Call ones, that's quite an interesting feature in C++. I'm not going to into it, but it's interesting because it's a non-trivial example of the memory model. We have some sequence of calls, and the visibility of changes is this not completely trivial graph. So that's the one that I like to show to the students. And then we get into the real meat, so the atomic operations, where we first just tell the students what the atomicity means, because let's say the compare exchange is not so trivial, so it also needs a bit of explaining. But then we get into the memory order enumeration in C++, which defines the different semantics of the atomic operations, so the acquire, release, relaxed, sequential consistency, and this stuff, where we spend most of the time on the release acquire, so which is this basically the same release acquire you get with the mutexes. So they are already a bit familiar with this, and they don't seem to be that surprised when we get to this in the atomics, where we spend quite some time with some examples of how to properly establish this release acquire semantic between operations, and how not to do it. So also show them some negative examples that look like they might be right, but they aren't. And yeah, so this discussion like this. So we try to explain it. We spend a lot of time explaining this, but still, from this, based on the assignment, some students still might struggle with some, let's say, more interesting cases. Then we also go to the happens before relation, which is the kind of core of the C++ memory model when you really get into the formal background. So what operations are guaranteed in what order, but we just explain this informally. So there's just one slide that I spent something like 15-20 minutes explaining it, of how this relation is defined and how it actually defines the memory model, so how it defines the visibility of the operations. And surprisingly, the students seem to actually be able to understand most of it. So now we also try to evaluate the stuff we did. So the course originally was taught without this memory focus on memory model. I think it was briefly mentioned at the end. So then we reorganize it. But we also made some other changes. So I can't really compare how focusing on the memory model has affected the lectures, because there's too much noise from the rest. But what we can tell from the student feedback and test results, that the results seem to be quite good. So the students seem to be able to program parallel C++ programs just as well as before, but now they also have some understanding of the memory model. So using some data from an assignment, they were supposed to use atomic variables for some synchronization, and the memory model was fairly important, so it was quite simple assignment, but the memory model was not completely straightforward. And so what the students did, so we're 35 students, 13 students used the acquire and release memory model for the atomic operations correctly. There was one student who specified sequential consistency, which is unnecessarily strong for the assignment, but it's also correct. And there were actually 2 students who correctly used relaxed consistency. So the assignment wasn't that strictly defined, and so they were able to present assumptions that would allow them to use the relaxed consistency. So 2 of them did this and correctly explained why they used relaxed, and there were 2 who used relaxed consistency, but they didn't really explain why they think this is correct. And then in this table, there are some missing students until this 35. So that's students who did not explicitly specify the memory order, but the default one in this case is correct because that's the sequential consistency, which is a bit too strong, but it's correct. So they still had to explain in the text why they claim that their solution is correct with regards to the memory model, but they didn't really use it in the code. So it's a bit unclear whether they actually understood it or not. Okay, and that's it. So we claim that the understanding of the memory model is important because once you start doing non-trivial C++ parallel stuff, you really need to do this properly. And based on our experience, think that it can be taught already in the introductory parallel computing course. So many people leave it at the end of some advanced course, and we start right away with it. And the students still seem to manage, and we don't need to spend that much more time on the lecture. So I think, added just one lecture, so one 90-minute lecture compared to the original state. Yeah, and that's it. So thank you for your attention. I think I was 1 or 2 minutes over, but sorry for that.
Okay, thanks, Jiri. Our next paper is, I've already been told I can just call them Sascha and Bart. And they're going to be talking about teaching complex algorithms.
Yeah, let me just share my screen. I hope you can see now everything nicely and so on. Okay, great.
Looks great, Bart. Looks great, Sascha.
All right, so then, without further ado, let's just, dive right into this. So I don't really have this kind of overall evaluation here, but the point is, so like I'm Sascha and the other one is Bartłomiej Przybylski. I'm from the Vienna University of Technology, so just like a few kilometers away from Jiri, just before, and the other one, the Bart, is from Poznan in Poland. So what are we going to talk about? So first, I will go through the course that we are teaching, then about the package that I'm introducing here and why this is helpful in order to teach approximation algorithms for scheduling problems. So what's our course on? So we call that course parallel algorithms, and parallel algorithms it's just a label. So we could basically do several things in there. Sometimes we do a few PRAM algorithms, sometimes we do scheduling. And this class here is a master's course for software engineering students. We could also call them computer science and computer engineering students. And here, this is some kind of a Venn diagram, what I think is appropriate to classify that class or this course here. So we are somehow in this intersection between scheduling theory, approximation algorithms, and parallel computing. So in the end, it's a parallel computing class. So what we do is we introduce basic scheduling theory, Graham's 3-field notation. What's the fundamental classification here? What are the basic concepts and scheduling problems that we are tackling in this domain? And then we basically come to the things what we are going to talk about are approximation algorithms for the same class of problems, scheduling problems for parallel machines. And then once we have covered and understand all the theoretical concepts, we go to applied. The theory that was somehow applied and that we covered in the theoretical setting, we now try to apply and practice. For example, how loop scheduling algorithms then are actually implemented in OpenMP, or how work stealing would work in Silk or OpenMP. And for doing that, we've created a package called scheduling.gl, which is a Julia package. That's why it's called JL. And the main purpose is really for education and research reasons. But research is maybe, I mean, only a second thing. It was actually done as an education project. You know, I've compiled a few programs here and there, and then in the end, we put all of them together and created that package. And it's really focused on parallel machine models and parallel machine scheduling. So we, in the Graham's notation, we have something like PC max and PNEC max. So we have regular identical parallel machines, like your multi-core machine, and you would like to minimize your make span, your schedule length. And what's interesting here is why we have that, because we implemented a few approximation algorithms for these particular problems to understand concepts. This is the important thing. So we actually implemented several polynomial time approximation schemes. So we have FP-TASes and P-TASes for these problems. And the killer feature for the Julia is that jump package. That is a Julia package for mixed integer programming, and this makes things really nice. So if you want to try scaling GL, you just start Julia, do package at scheduling, and you get this scaling GL package installed, and you can start using it. So what are we actually trying to teach here? We're trying to teach concepts. So what are the basic lower and upper bounds for these scheduling problems? For example, really basic ones, Graham's this scheduling algorithm. And then we are trying to tell them what are the techniques in order to devise these approximation algorithms for scheduling jobs. Then we come to the problem of, once we had the sequential jobs, we move to parallel jobs, because there's somehow a connection between them. And also we would like to show that when you consider the problem of scheduling parallel jobs, there's a huge relationship to strip packing problems. And once you have all this, I mean, in the end, we are trying to do something in practice here. So we would like to understand the practical consequences of when you do something in terms of solving a scheduling problem, when you have heuristics, solution quality, time to solution, when you have approximation algorithms or schemes, how they work in terms of solution quality, which is somehow guaranteed, but also how long it takes, and of course, exact algorithms. So what's the problem now? The problem is at least what I claim here, that teaching these approximation algorithms for scheduling problems is hard. I mean, people zoom out and do something else. And because most of the time, these algorithms are not intuitive at all. They are made for the bound, but they're not made as for educational purposes. And the ideas only come somehow, you understand them only after a certain amount of time. So the claim is, what really helps to understand them when you interact with these approximation algorithms and visualizing their results. And this scheduling JL package provides exactly that. And what's somehow new, what I have not seen that much, is really provide implementations that usually would not be implemented. Several P-TASes, FP-TASes, and things like this that theoreticians don't care about implementing, and practitioners also don't care about, but in order to understand the theory better, implementing them helps a lot and has been extremely rewarding to the students and to me. So let's just look into this. So when one goal that I had is understand bounds. So what do I mean by this? So there's a nice website. It's called the Scheduling Zoo by Christophe Dürr of Sorbonne University in France. And if you're interested in any of these scheduling problems, you can just go here to this website and choose your problem that you're interested in. Maybe you would like to know identical machines, and you want to minimize the make span. And then it gives you the result is here. It tells you all the knowledge. I mean, there's more, but I just cut this list of theoretical knowledge that you have for the particular problem. For example, here, PC Max, it says it's strongly NP-hard, and it was shown by Gary and Johnson. And then it's a fixed parameter tractable. It was also shown here and there. Or we can actually devise an EP-TAS for that problem. And but the problem is, well, that's not a problem, and that's nice, but you don't have an implementation of these things. And this is somehow what we are trying to provide here. So objective. One objective is, really understanding the tightness of bounds, because that seems to be a problem for many students. So what we are trying to tell them, okay, go try to find some approximation algorithm that we have and try to come up with a worst case instance. And so we experiment with this. So we, for example, here have a regular LPT heuristic where we just sort the jobs by the largest processing time and then schedule on the least loaded machine. So we would come up, I mean, this is the worst case example for that problem. But the point is, even if we show this is the worst case example, we tell the students, okay, try to find another one, or try to see if there's any structure in that instance to make it look particularly bad. And we also have a way of computing the exact solutions, which works for small instances, but then they can compare, and it really helps them to understand what it really means to get these kind of bounds. So, and then a huge problem is understanding online algorithms, especially the best ones. So objective here, we're trying to understand these online algorithms, and we do this by actually dynamically creating these schedules. And that has helped, and that's also part of scheduling.jl. One particular example is, again, for the problem of PC Max, we have the best possible, I mean, not best possible, best known algorithm by Fleischer and Wall, which is 1.92 competitive, and which it's called, and there's a C missing, MR. Anyway, so that's, and this algorithm is not intuitive at all. You can look into this, it's kind of strange at first glance. But once you have that, and you somehow see how the schedule is built, and you're trying to go through the algorithmic steps, and you see somehow what it's trying to do, that it always tries to somehow keep some space for long tasks, because you never know when this schedule has to stop. So if you have a really long task, you can hide it somewhere. And at the same time, you try not to increase this gap too much, not to make it too steep, so that if now the sequence of jobs would stop, that you somehow miss your bound. So you don't want to be larger than 1.92. And this visualization thing and playing with the algorithm has helped a lot in order to, like, when I taught this before, people just in the exam, we do this oral. That's the problem here. So I have this oral feedback, and once we had all this kind of thing in place, it was much easier to for them to understand and then to tell me the concepts. But let's say the most important thing here is really the understanding the art of epsilon, choosing epsilon for approximation schemes. So we are trying to come up with approximation schemes for scheduling problems which have a performance guarantee of 1 plus epsilon, like this. So epsilon. So epsilon somehow changes something. Most of the time when we choose an epsilon, the algorithm does something. It usually modifies the instance in some way or the other. It makes large instances smaller and so on, making sure that we still get to this performance guarantee. So students should now experiment with this p-tasks and try to see how modifying this epsilon actually changes these instances and get this feedback, and also how it then changes the running time. Okay, so one example is this. We look into the p-task that was proposed by Schurman and Wögiger in this tutorial on approximation schemes. And here it's just 2 machines, classical problem, 2 machine scheduling. It's basically taught in all the scheduling classes. We try to minimize the make span, and we try to do that here by input structuring. So input structuring in this case just means we have a lot of jobs. We choose an epsilon, and then we can classify the jobs into small and large jobs. And all the small jobs are so small that they are somehow bounded by epsilon. And we can just glue all these small jobs together and make the instance easier. So we reduce the number of instances. When I teach that to the students, yeah, they somehow get the idea, but when they play with that algorithm and actually get the feedback, because we basically get that internal feedback when you run this, you get graphs like this, like charts. So this is the original instance. So we have 10 jobs in the beginning, 100, 1,000, and 10,000. And here's the number of jobs in the simplified instance for the p-task. And depending on the epsilon, they actually then see that when you choose a bound of 1%, yeah, you still reduce heavily, but you have much less, much more tasks to consider than well, for example, here with a 50% gap, and this is really valuable. The other thing is, and there's a lot of things in this graph. So we have here an FP task for the same problem, and the FP task has a better running time. Obviously, it's fully polynomial, but the approach is somehow it does a dynamic program, and on the way it gathers some auxiliary data. So it tries to take all these states, and you're trying not to have the state explosion, so that you get into exponentially many states. So your epsilon is basically helping you to how much you reduce in this auxiliary data. And then when you analyze your running time versus the different things, so you have here this SW3 algorithm with different numbers of different precision. So 10%, 25%, 50%. Well, you see obviously that when the closer you get to the optimum, you will pay with running time. Okay, that's not so hard. And also that the LPT, which is some heuristic here, which provides you a larger bound, that especially for small numbers of jobs, this year, the size of the circle denotes the approximation ratio for that instance. I mean, it's 2% off, but still, I mean, the point is you get a bit larger. The make spans are a bit larger with LPT, but still LPT is really fast. And also in this case, opt is really fast. So that's also something to take away from these kind of things. When you have nicely structured problems like this, then the solvers, although that's NP hard, will do a very good job. And here with Gurobi, it's actually not worth to use an FP task. So how much time do I have left? Just to make sure, 5 minutes, 10 minutes, 10 minutes, I guess, right? So
about 3 minutes, actually.
Sascha. Oh, okay, 3. That's okay. I will speed up here a little. So, and then we have one thing that is what I like. I mean, what I like about scheduling.jl is this dual approximation algorithm, which was proposed by Hochbaum-Schmois for PC Max. And the idea here is that in order to get this p-task, we don't solve this scheduling problem directly. What we do is we solve the dual problem, and then the dual problem is a bin packing problem, and we solve it approximately. And by doing this, we can then translate our solution into a scheduling problem. It basically comes down to a bin packing problem with a fixed number of piece sizes. So all the pieces that you need to pack, or let's say in a bin, they are fixed. There's not infinite the number, many different numbers. And then that you can basically come up with p-tasks, and they came up with this. And but that's particularly heavy somehow. When you play with this, then first of all, the students, they look into the structure, what you can get when you play with the epsilon, and also how long it takes to do this, and how complicated it is to get these kind of dynamic programs running in practice. All right, so we have a few other things, but in conclusion here, so teaching these scheduling algorithms, especially approximation algorithms, has been pretty hard. I mean, to keep students motivated all the time, and before they actually see the full picture, you have to introduce lots of notation. And especially, it is hard to understand these theoretical concepts just by looking at the math. And they look, yeah, it makes sense. Yeah, you come up with this bound, yeah, but when you then try to talk to them, especially in the exam, and like try to what's the actual idea of that algorithm? They have no clue. They can do the math, but the structure of the problem is not being there. Once we use that kind of scheduling.jl so that they play with these algorithms, this has changed. I mean, at least for me. So I don't have a scientific proof of this. So that's what, and Julia was a perfect choice for this, because it's simple to use. It's like some MATLAB-like, and it's really fast. It's nice. So for EduPar, we actually bumped up the version here. So we put everything into 0.20, and we actually also have these kind of things in here. It's an EP task and that's a beta version. It's not in the main branch yet, and we are trying to, because it's kind of hard to implement these kind of things correctly. And once we have this, it's also a good source of, you know, how would you do this and compare to heuristics. All right. So thanks for your attention and thanks for having me.
Okay, thank you to both of the speakers. Again, we're going to do questions in the chat. So if you've got questions for either of the speakers, please do get started. There was a couple questions for Sascha, the second speaker. Did you have a reason that you were not covering other kinds of scheduling problems, the dependencies, batch scheduling, other things? Do you plan on doing that?
We do that, to be honest. So we do this in the class, but you know, when, well, like having all of these, they already, you know, cover a lot of, you know, a lot of material. That's the point. So with dependencies, it's just one lecture, and batch scanning, we do that as well, but that's heuristically. I mean, that this batch scheduling in Slurm, we do that, but there's not really something to understand. In structure, it's really easy to understand these kind of things. I mean, at least that's what I claim. Tell me if I'm wrong. And the other one is, yeah, they have to implement scheduling algorithms too. They have to come up with something that's somehow related to the keynotes, because it's, you know, about frequency scaling. They not only have to decide where things are, but also in what kind of frequency these jobs run, in order to, you know, it's a bi-criteria problem, to minimize make span and to minimize energy. And it's usually you have to have some kind of trade-off. And the interesting thing is, I don't know if you have the same kind of like experience, like in the bachelor classes, undergrads, they implement NP-hard, you know, heuristics for that, or this kind of branch and bound stuff for knapsack. But once they actually have an NP-hard problem, they really have a hard time. They always think they can get away with enumerating the entire search space and somehow come up with this, because it looks so innocent. 100 jobs, 20 machines. Yeah, we can just try all combinations and we are good. And well, before with scheduling GL, they already learned a lesson, because also with p-tests they won't get away with this.
And then I had a higher level question for the first speaker. You sort of wanted to do the memory model, right, sort of everywhere. And I was wondering how that would look in the curricular recommendations, right? It sort of seems like it can't be a separate line item, or at least it needs to be referred to elsewhere. Do you have a recommendation for what we should do for recommendations?
Yeah, good question, but I have to admit I haven't really thought about it. So yeah, so because the point is not to have it as a separate point, but rather kind of weave it into it. So yeah, it's not a new topic to do. It's a different way of doing the existing stuff. So yeah, there's a lot of text in the curriculum, I guess, so there would be maybe some space, but.
Well, I think it was, I mean, we were trying to do examples for things, right? And so it seems like some of those examples that you had, or things like them, need to go in there somewhere, but I'm not quite sure how to do that. So I think it's an interesting problem. And then for Sascha, you did bring up at the end, you talked about sort of bachelor classes. What about a class that's not, you know, so like I don't teach a scheduling class, right? What could I bring in, you know, as a small bit, right? If I want to do some of the scheduling, is there anything that you've learned or seen that would be helpful?
For undergrads?
Yeah.
I mean, you could basically use the general notions that are implemented, their general algorithms, as shortest job first and largest processing time, and these kind of heuristics. I mean, like it always helps to understand these kind of things. But it's really done for, it could be used there. I mean, in the end, for all kinds of approximation algorithms, you have that problem, and we basically use scheduling to teach approximation schemes. I mean, that's somehow that's our somehow that's our theme. And it could be changed, but it's really something that we need somehow. Complexity theory, you need to understand some things about machines, and it's too complicated, I guess. There's too much for an undergrad class for this kind of like p-tasks that it needs a bit of preparation.
Right. Yeah. But it looked like, so the tool actually does a lot of visualization though, right? That would be helpful at least.
That is true, yeah. And it outputs this nice TXZ LaTeX things, and you can just put it into your paper if you like.
So I could use it to make slides, at least. But
You
okay.
could try. Maybe, I mean, like, I think the visualization part is not the strongest one, I guess, but the strongest part of the package. But anyway, it's free. I mean, like, people just can contribute and contribute things to it.
Okay, are there other questions? Give people a minute if they're typing here. Okay, I think let's thank the speakers. Okay, it does not sound good not in a group, but thank you very much for two very interesting talks, and the papers are very interesting. So,
Thank you for having me.
thank you.
Yeah, thank you.
Okay, so that is the end of this session.